Imagine if I told you that the ground beneath you is actually alive. It doesn't breathe like we do, but it moves, slowly, quietly, every single moment. Beneath your feet, rocks are hiding secrets, secrets older than human history itself. This place you're in right now may have once been under an ancient ocean. It may have been buried beneath massive walls of ice, and long ago, it may have been surrounded by rivers of fire. Earth may look calm, but the truth is, Earth never truly sleeps. It simply changes, very slowly, over time. And tonight, we're going to step into that peaceful, mysterious world of Earth science, where every mountain, every river, and every breath of wind has a story to tell. If you enjoy these relaxing science journeys, take a moment to gently tap like and subscribe to stay with us for more calming nights like this. And tell me in the comments what helps you relax the most: the sound of rain, the ocean, or the quiet mountains. But for now, just slow your breathing, let your body soften, and allow your mind to drift. Welcome to the most relaxing journey across our planet. Let's begin. Tonight, let your mind drift towards something calm, ancient, and quietly powerful. Not the busy world of people and noise, but the slow world beneath your feet. The world of Earth science, where every stone holds a memory, and every landscape is part of a story still being written. Earth may look still, but it is never truly resting. The planet is always moving, always reshaping itself, even when the surface seems peaceful. Mountains rise, oceans shift, rivers change their paths, and invisible forces deep underground continue their endless work. Far below the continents, Earth's crust is broken into massive plates. These plates are not fixed in place. They drift slowly across the planet, only a few centimeters each year. That motion sounds small, almost meaningless, but when you give it millions of years, it becomes strong enough to build the tallest mountains on Earth and carve entire coastlines into new shapes. Out in the deep ocean, new land is being created right now. Along long underwater mountain chains called mid-ocean ridges, molten rock rises through cracks in the seafloor. The lava meets freezing seawater and cools instantly, hardening into fresh basalt. This process is so quiet and hidden that most people never think about it, yet it is one of the main ways Earth renews its surface. At the same time, in other parts of the ocean, the seafloor is disappearing. In deep trenches, one tectonic plate bends and slides beneath another. This is called subduction. The seafloor sinks slowly into the mantle, where it melts and becomes part of the planet again. Earth is constantly recycling itself, like a living system that rebuilds its own skin. Sometimes this movement becomes dangerous. When plates lock together, pressure can build for centuries. Then, in a sudden moment, that stored energy releases as an earthquake. If the seafloor shifts upward or downward during the quake, the ocean above it moves too. That movement can create a tsunami. In deep water, a tsunami is not a giant wave. It is a long, low swell traveling across the ocean at incredible speed. Ships might barely notice it passing beneath them, but as it approaches land, the water becomes shallow, the wave slows, and its energy rises upward. The ocean can suddenly pull back from the shore, exposing seafloor that is normally hidden, and then the surge arrives. The quiet truth is this: Earth's beauty comes from motion. Every cliff, every valley, and every beach and every island exists because the planet never stops shaping itself. And as we continue, We'll explore more of these slow, powerful processes, letting the story of Earth unfold gently, one peaceful fact at a time. As Earth continues its slow motion beneath the oceans, the continents above are also drifting, almost like giant rafts on a hidden current. They move so quietly that you would never notice in a single lifetime. But the planet measures time differently than we do. For Earth, 1,000,000 years is like a soft blink. When two continents meet, they do not slide smoothly past each other. Instead, they press together with enormous force. Neither continent wants to sink easily, because continental crust is lighter and more buoyant than ocean crust. So the rock begins to crumple and fold, thickening upward like a carpet pushed against a wall. This is how mountain ranges are born. The Himalayas are one of the most dramatic examples. India is still pushing northward into Asia today. That slow collision continues to lift the mountains higher, even now. The peaks rise by tiny amounts each year, but over long spans of time, those tiny changes become breathtaking. The tallest mountains on Earth are not simply standing still, they are still being built. But mountains are not permanent monuments. As soon as they rise, they begin to fall. Wind, rain, snow, and ice slowly wear them down. Rivers cut into their slopes, carrying away grains of rock. Glaciers scrape and grind the surface, dragging stones like sandpaper across the land. Earth is always balancing creation and destruction. Mountains grow through tectonic pressure, and they shrink through erosion. This slow cycle can reshape entire river systems. A river flows downhill, guided by gravity, but the land itself can tilt and change. If a mountain range rises or a region slowly lifts, the slope of the land can shift. Sometimes the river's downhill path becomes weaker, and the water begins searching for a new route. Over time, another river system with a steeper drop can capture that water, pulling it into a different basin. This process is called river capture, and it can completely reverse the direction of a river. Valleys that once carried strong flowing water can become dry and silent. New channels form, and sediment that once traveled toward one coastline may suddenly be redirected toward another. The landscape, in a way, competes for water. Drainage basins expand and shrink like living territories. You can sometimes see clues of this ancient struggle. A dry valley may appear far too wide for the small stream that remains inside it. Sharp bends in a river may look strange, almost unnatural, until you realize the river was forced to change direction long ago. Even the calmest stream has a history of conflict written into its curves. And while rivers quietly rewrite the surface of continents, another kind of force is shaping Earth in hidden ways. Deep underground, pressure is building, heat is rising, and in some places, the planet finds an escape. Soon, we will drift toward the world of volcanoes, where Earth releases its inner energy into the open air. Volcanoes may seem like rare events, but in truth, Earth is covered with them. Most are simply hidden from human eyes. They are not always towering mountains with glowing lava. Many are quiet cracks on the ocean floor, slowly building new crust in the darkness. Underwater volcanoes are the most common type on the planet. Along mid-ocean ridges, magma rises and cools almost instantly, forming long stretches of fresh rock. Because of the pressure of deep water, gases remain trapped inside the lava, so eruptions often look smooth and gentle. The molten rock can ooze outward in rounded shapes called pillow lava, stacking layer upon layer like slow-moving bubbles frozen in time. In some areas, seawater seeps down into newly formed crust. It travels deep into the rock, where it is heated by the planet's inner warmth. Then, it rises back up through vents, carrying dissolved minerals. These hydrothermal vents can build tall chimneys made of metal-rich deposits, and they create an environment unlike anything on the surface. Even without sunlight, life can thrive there, powered by chemistry. Strange ecosystems form around these vents, feeding on energy released from Earth itself. Not all volcanoes erupt molten rock. Some release mud, others release ice. Mud volcanoes are driven by pressurized water and gas trapped in sediments. Instead of lava, they push up thick, bubbling mud. These eruptions can happen suddenly, creating small cones, cracking roads, and covering land with sticky gray flows. Some mud volcanoes continue for years, quietly releasing methane into the air, reminding us that Earth can erupt in many different ways. In colder environments, Earth can even produce cryovolcanic activity, where slush and frozen chemicals behave like lava. While cryovolcanoes are more famous on icy moons like Europa or Enceladus, the idea shows something fascinating. Volcanoes are not defined by fire alone. They are defined by pressure, heat, and the need for the planet to release what is trapped inside. Sometimes, volcanic material travels far beyond the eruption itself. Volcanic ash is not just dust. It can carry tiny nutrients, especially iron, which many parts of the ocean lack. When ash falls onto the sea, those particles can dissolve and fertilize surface waters. Under the right conditions, plankton blooms can explode into life, turning the ocean greener and feeding the base of the marine web food. This means a volcano on land can briefly influence life far offshore. Fish, seabirds, and larger predators may follow the sudden abundance. A distant eruption can quietly ripple through ecosystems, not through flames, but through a thin veil of mineral powder drifting across the sky. Even desert dust can do something similar. Winds can lift fine particles into the atmosphere and carry them across entire oceans. That dust may contain phosphorus and iron, which can nourish rainforests and marine life thousands of miles away. Earth moves nutrients the way it moves water, connecting dry deserts to living forests. And while volcanoes shape the surface, another force is working even deeper. Beneath the mantle, in a hidden ocean of metal, Earth is generating something invisible but essential. Next, we'll drift toward the planet's core and the magnetic shield that quietly protects the world above. Deep beneath the crust and mantle, far beyond any place humans could ever reach, Earth hides a strange and powerful secret. At the center of the planet is a core made mostly of iron. Part of it is solid and part of it is liquid. And in that liquid layer, something extraordinary is happening. The outer core is like an ocean of molten metal. It flows, swirls, and circulates as Earth slowly cools over time. This movement is not random. Earth's rotation helps organize the flow, shaping it into patterns that can last for centuries. And because molten iron conducts electricity, these moving currents generate a magnetic field. This process is called the geodynamo. It is one of the most important systems on the planet, even though we never see it directly. The outside of Earth stretches far into space, forming a protective bubble around Earth known as the magnetosphere. It is an invisible shield that deflects many of the charged particles constantly streaming outward from the sun. This solar wind is always present, like a cosmic breeze, but sometimes the sun becomes violent. Solar flares and coronal mass ejections can launch powerful storms of particles and energy toward Earth. Without a strong magnetic field, those particles would slam directly into the atmosphere. Over long periods of time, they could strip away gases, thinning the air and making the surface more hostile to life. The magnetic field does not block everything, but it redirects much of the solar wind, reducing the damage and helping Earth keep its atmosphere stable. This is one reason Earth remains so life-friendly. A comparison with Mars makes the idea even more striking. Mars once had a thicker atmosphere and liquid water on its surface, but today it has only weak, patchy magnetic protection. Over time, solar particles have helped erode much of its atmosphere. Mars became colder, drier, and far less welcoming. Earth's magnetic field, in a quiet way, may have helped protect the conditions needed for oceans, clouds, and life to continue. The magnetic field is not perfectly steady. It drifts, shifts, and changes strength over time. In some regions, it weakens. In others, it strengthens. The poles themselves can wander slowly across the planet, and across deep time, the field has even reversed completely, with north and south switching places. These reversals do not happen overnight. They unfold gradually over thousands of years, like a slow turning of a cosmic compass. Sometimes, the magnetic field reveals itself in beauty. When solar particles do manage to enter the atmosphere, they are guided along magnetic field lines toward the polar regions. There, they collide with atoms of oxygen and nitrogen high above the clouds. Those collisions excite the gases, and as they return to normal, they release light. Green, red, purple, and blue curtains spread across the sky, moving like silent waves. These auroras are space weather made visible. They are reminders that Earth is not isolated. The planet is constantly interacting with the sun, with space, and with invisible forces far beyond our atmosphere. And as we continue, we will drift even farther outward, toward rocks that fall from the sky, carrying messages from before Earth even existed.
Not every rock on Earth was born here. Some arrive from the darkness of space, falling through the atmosphere as glowing streaks of fire. These are meteorites, and they are far more than ordinary stones. They are fragments of ancient worlds, pieces of the solar system that never became planets. When a meteorite lands on Earth, it can carry time inside it. Some meteorites contain grains that are older than Earth itself. These tiny mineral fragments are called pre-solar grains. They did not form around our sun. They formed around other stars, long before our solar system existed. In distant stellar atmospheres, in the violent winds of dying suns, and in the explosive shock of supernovas, these grains were forged. Then they drifted through interstellar space for ages, surviving radiation, collisions, and cold emptiness. Later, when the cloud of gas and dust that would become our solar system began to collapse, a small portion of that ancient stardust was swept into the forming disk. Most of it was melted and mixed into new material, but some grains survived. They became trapped inside asteroids, sealed away like microscopic fossils of the universe. Billions of years later, when those asteroids break apart, their fragments can fall to Earth. A rock that lands quietly in a field might contain particles that existed before the sun was born. Scientists can identify these grains by their unusual isotope signatures, chemical fingerprints that do not match anything formed in our solar system. It is a strange thought. You could hold a meteorite in your hand, and inside it might be a piece of a star that died long before Earth ever formed. Sometimes these visitors from space leave larger marks. When an asteroid strikes Earth, it can carve an impact crater into the surface. A fresh crater can be obvious, a circular scar with a raised rim and shattered rock. But Earth is not good at preserving these wounds. Over time, wind and water smooth the edges. Sediment fills the depression. Forests grow over the shape. Rivers cut through the rim. In the oceans, craters can vanish beneath layers of mud and sand. Many impact craters are hidden so well that scientists only discovered them by noticing strange circular patterns, unusual rocks, or gravity anomalies. Some were confirmed only after drilling deep cores into the ground and finding melted rock layers and shocked minerals. Shock is one of the clearest signatures of an impact. In a collision, pressure rises so violently that ordinary minerals transform instantly. Quartz can develop microscopic lines called shock lamellae, tiny parallel features that cannot form through normal geology. In some cases, quartz changes into high-pressure forms that only exist during extreme events. These minerals are like forensic evidence. Even if a crater erodes away, the shock remains, quietly proving that something from space once struck the planet. This means Earth has likely been hit far more times than our maps reveal. The surface is constantly erasing its own history. And yet, even when the scars fade, the consequences can remain. Impacts have shaped evolution, altered climates, and rewritten life's path. As we move forward, we will explore another hidden part of Earth's story, not from the sky, but from deep time locked inside ancient rocks beneath our feet. If you could peel back Earth like the pages of a book, you would find that every layer is a chapter. Some chapters are young, written recently by rivers and storms. Others are unimaginably old, written when the planet was still forming its first crust. The oldest rocks on Earth are not found on the ocean floor. Ocean crust is constantly being recycled. It forms at mid-ocean ridges and sinks back into the mantle at subduction zones. Because of this endless cycle, most ocean crust is relatively young in geological terms, usually less than 200 million years old. Continental crust is different. It is lighter and more buoyant, and it resists being pulled downward into the mantle. That is why continents can survive for billions of years, carrying fragments of Earth's earliest history beneath their surface. In some places, geologists have found rocks that are more than 4 billion years old. These rocks formed not long after Earth itself formed. They are rare, but they exist, preserved in stable regions of continents called cratons. These cratons are like the deep roots of the continents, thick, ancient, and difficult to destroy. The age of a rock is not guessed by its appearance. Scientists measure it through radioactive decay. Certain minerals, such as zircon, trap radioactive atoms when they form. Over time, those atoms decay into other elements at a predictable rate. By measuring the ratio of parent atoms to daughter atoms, scientists can calculate how long the mineral has existed. It is like a clock built into the crystal structure itself. Zircon is especially valuable because it is tough. It can survive erosion, heat, and pressure. Some zircon crystals have been found that are older than any known rock formation, meaning they may have survived multiple cycles of destruction and rebuilding. These tiny crystals are some of the oldest objects on Earth, carrying chemical hints about the early planet's oceans and atmosphere. Ancient rocks also hold evidence of vanished worlds. Coal seams, for example, are more than fuel. They are compressed plant material from ancient swamps and wetlands. Long ago, thick forests grew in waterlogged basins where dead vegetation piled up faster than it could decay. Over time, that plant matter became peat. As sediment buried it deeper, heat and pressure slowly drove out water and gases, leaving behind carbon-rich rock. When miners cut into coal, they sometimes find leaf patterns and plant impressions preserved with surprising clarity, like a shadow of a lost forest pressed into stone. Oil has a different origin, but it is also a story of life transformed. Much oil began as microscopic organisms drifting in ancient seas and lakes. When they died, they settled into mud where oxygen was limited. Over millions of years, as sediment buried them deeper, heat slowly broke down their organic molecules and rearranged them into hydrocarbons. The oil then migrated through pores in rock until it became trapped beneath a sealing layer. An oil reservoir is not an underground lake. It is oil stored in tiny spaces between grains of rock, hidden in darkness. All of these materials are reminders that Earth stores time in physical form. Plants become rock, microbes become fuel, seas vanish and leave behind fossils, mountains rise, then erode into sand. And beneath all of it, the planet continues to shift. Next, we will follow the slow movement of Earth's climate through deep time and the quiet ways the planet can change its own atmosphere.
Earth's climate feels familiar because we live inside it every day. We know the warmth of sunlight, the coolness of rain, the weight of humid air before a storm. But the climate you know is only one version of Earth. Over deep time, the planet has worn many different atmospheres, many different temperatures, and many different skies. Sometimes, Earth has been far warmer than today. At other times, ice has spread across continents, covering the land in glaciers so vast that the world looked almost colorless from space. These shifts did not happen randomly. They were driven by slow changes in oceans, continents, volcanic activity, and even the orbit of Earth around the Sun. One of the most powerful climate forces comes from volcanoes. When a major eruption occurs, it does more than pour out lava. It can inject gases high into the atmosphere. Sulfur-rich gases can rise into the stratosphere, where they transform into tiny droplets called aerosols. These aerosols reflect sunlight back into space. Instead of warming the surface, sunlight is scattered away, and the planet cools. This cooling can last for months or even years, depending on how much material enters the upper atmosphere. Unlike ash, which often falls out quickly, stratospheric aerosols can spread around the globe and linger. The result can be cooler summers, altered rainfall patterns, and changes that affect crops and ecosystems far from the eruption itself. Sometimes the effects are recorded quietly in nature. Tree rings may show slower growth. Ice cores may preserve thin layers of volcanic material. Even historical records describe unusual sunsets, painted red and purple by particles drifting in the sky. Earth's climate can also shift through the movement of continents. When continents drift, they change the flow of ocean currents. Ocean currents carry heat around the world like slow rivers of warmth. If a landmass blocks a current, it can cool one region and warm another.
If a seaway opens, it can allow water to circulate in new patterns, changing global climate over long spans of time. Ice ages are influenced by another gentle factor, the shape of Earth's orbit. Earth does not orbit the Sun in a perfect circle. Its path stretches and relaxes over long cycles. The tilt of Earth's axis also changes slightly, and the direction of that tilt slowly wobbles like a spinning top. These cycles affect how sunlight is distributed across seasons and latitudes. They do not create ice ages alone, but they can trigger them when conditions are already close to a tipping point. When ice expands, it reflects sunlight. Ice is bright, and it sends much of the sun's energy back into space. This creates a feedback loop. More ice leads to more reflection, which leads to cooler temperatures, which allows even more ice to form. In this way, a slow shift can become a powerful transformation. But Earth also has warming feedbacks. Carbon dioxide and methane trap heat. When volcanic activity increases or when organic material breaks down, greenhouse gases can rise. Warmer oceans can release more carbon dioxide. Permafrost can thaw and release methane. The climate system is full of connections, each one pulling gently on another. Earth's atmosphere is not a fixed blanket. It is a living, shifting layer shaped by geology, chemistry, and life itself. And in the next part, we will drift into the oceans, where water stores heat, carries nutrients, and quietly controls much of the planet's breathing. The oceans are Earth's largest memory. They store heat, move energy across the planet, and hold chemical traces of ancient climates. When you look at the sea, it may seem like a single endless surface, but beneath that surface is a layered world, with currents moving like slow, invisible rivers. The ocean does not just sit still, it circulates constantly. Some currents are driven by wind, creating broad surface flows that can travel across entire basins. Other currents are driven by differences in temperature and salt. Cold water is denser than warm water. Salty water is denser than fresh water. When water becomes cold and salty enough, it sinks, sliding downward into the deep ocean like a slow waterfall. This sinking and rising forms a global system called thermohaline circulation, sometimes described as the ocean's conveyor belt. It moves water around the planet over hundreds or even thousands of years. This circulation helps regulate climate, carrying warmth from the tropics toward higher latitudes and balancing Earth's temperature. The ocean also stores heat far more effectively than air. Water can absorb large amounts of energy without changing temperature quickly. This is why coastal regions often have milder climates than inland areas. The ocean acts like a giant thermal buffer, smoothing out extremes. But the ocean's calm appearance hides sudden power. Tsunamis, for example, are one of the fastest ways energy can move across Earth. They are not normal waves created by wind. They are often triggered by earthquakes, landslides, or volcanic collapses that suddenly displace massive amounts of water. In deep ocean water, a tsunami wave can be long and low, spreading across a huge distance. The energy travels faster than most jetliners. Yet the surface rise may be so subtle that ships pass over it without realizing anything unusual is happening. As the tsunami reaches shallow coastal water, the wave slows, the energy compresses upward, the height grows, and what was once a quiet swell becomes a violent surge. Sometimes the ocean pulls back first, revealing the seafloor,
giving a brief and eerie warning before the wave arrives. The ocean is also connected to life in surprising ways. Volcanic ash, carried by wind, can fall into the sea and fertilize it. Ash often contains iron, a nutrient that plankton need in tiny amounts. When iron becomes available, plankton can bloom, spreading like a green stain across the water. These microscopic organisms form the foundation of the marine web food. A short bloom can feed fish, which feed seabirds, which feed larger predators. Even desert dust can play a similar role. Fine mineral particles can travel across oceans, delivering phosphorus and iron to regions that would otherwise be nutrient-poor. In this way, the world connects itself. A storm in one continent can quietly influence life on another. The ocean also preserves history. Sediments settle slowly onto the seafloor, building layers over time. These layers contain shells, minerals, and chemical signals that reveal past temperatures and past atmospheres. Scientists drill deep into ocean sediments like reading a timeline, uncovering evidence of ice ages, warm periods, and ancient shifts in circulation. The sea is not only water, it is a living archive. And as we continue, we will move from the ocean's surface to something even more delicate, the air above it, where Earth's atmosphere breathes, circulates, and shapes the world you feel around you.
Above the oceans and continents, wrapped gently around the planet, is a thin layer of air that makes life possible. Earth's atmosphere may feel endless when you look up, but compared to the size of the planet, it is surprisingly fragile. If Earth were the size of a basketball, the breathable part of the atmosphere would be thinner than a sheet of paper. And yet, this thin veil controls temperature, weather, and the movement of water across the world. The atmosphere is always in motion. Warm air rises, cold air sinks. The sun heats the equator more strongly than the poles, creating a constant imbalance. Earth responds by moving air in great circulation patterns, transferring heat like a slow planetary heartbeat. This is why winds exist. Some winds are gentle, like a sea breeze. Others are powerful enough to shape coastlines and lift dust across continents. High above the surface, jet streams race around the globe, narrow rivers of fast-moving air that influence storms and rainfall patterns below. Weather is the atmosphere's short-term mood. Climate is its long-term personality. One of the most important processes in the atmosphere is the water cycle. Sunlight evaporates water from oceans, lakes, and soil. That invisible vapor rises into cooler air, where it condenses into clouds. Those clouds drift until they release rain or snow, returning water back to the surface. Rivers then carry it back towards the sea, completing the loop. This cycle is so familiar that it can feel ordinary, but it is one of the most powerful forces shaping Earth's surface. Rain breaks down rock, snow feeds glaciers, floods carry sediment and carve valleys. Over millions of years, water has sculpted landscapes as effectively as tectonic forces. The atmosphere also acts as a protective shield. High above the clouds, the ozone layer absorbs much of the sun's harmful ultraviolet radiation. Without it, sunlight would damage living cells far more intensely, making life on land difficult. The atmosphere also burns up most small meteoroids before they reach the ground, turning them into harmless streaks of light. But the atmosphere is not only protection, it is also a balancing system. Greenhouse gases, such as carbon dioxide, methane, and water vapor, trap heat.
Without this natural greenhouse effect, Earth would be a frozen world, far too cold for oceans of liquid water. The warmth you feel at night, the gentle stability of Earth's temperature, is partly because the atmosphere holds energy instead of letting it escape into space. However, this balance is sensitive. Small changes in greenhouse gases can shift global temperatures over time. Volcanic eruptions can cool the planet temporarily by injecting aerosols into the stratosphere. Meanwhile, long-term shifts in carbon dioxide can warm or cool Earth across thousands or millions of years. The atmosphere is always responding, always adjusting. Even the air you breathe is tied to geology. Volcanoes release gases from deep within Earth. Weathering of rocks can remove carbon dioxide from the air. Oceans absorb gases and release them back again. Life itself reshapes the atmosphere by producing oxygen and altering chemical cycles. The air is not separate from Earth, it is part of the same living system. And as we move forward, we will explore a quieter kind of history, the hidden record stored in ice, where ancient air bubbles still whisper the climate of long-vanished worlds.
In the coldest regions of Earth, time can become trapped. Snow falls season after season, and instead of melting away completely, it slowly compresses into ice. Layer by layer, year after year, glaciers and ice sheets grow thicker, forming some of the most powerful natural archives on the planet. Ice is not just frozen water, it is a record. As snow piles up, it captures tiny particles from the atmosphere. Dust, ash, sea salt, and even pollution can become sealed inside. More importantly, small bubbles of ancient air are trapped between the grains. Over time, as the snow turns into solid ice, those bubbles remain preserved, holding samples of Earth's past atmosphere like tiny glass capsules. Scientists drill deep into ice sheets in places like Antarctica and Greenland, pulling out long cylinders called ice cores. These cores are like timelines. Each layer represents a different period, and by analyzing the gases inside, researchers can reconstruct past temperatures and past levels of carbon dioxide and methane. Some ice cores reach back hundreds of thousands of years. They show a repeating rhythm of ice ages and warmer interglacial periods. During ice ages, carbon dioxide levels were lower, temperatures dropped, and ice expanded. During warm periods, greenhouse gases rose, ice retreated, and oceans warmed. The ice reveals that Earth's climate naturally shifts over long spans of time, driven by complex interactions between sunlight, oceans, and atmospheric chemistry. Ice also preserves evidence of sudden events. A volcanic eruption can leave a thin layer of ash inside an ice core, marking the moment when particles spread across the globe. Some eruptions were so powerful that they cooled Earth for years, altering rainfall patterns and shortening growing seasons. In the ice, these events appear like quiet, dark lines, reminders that the planet's surface and atmosphere can change quickly. Glaciers themselves are also sculptors of land. When ice moves, it does not glide smoothly like water. It flows slowly under its own weight, and as it moves, it drags rocks and debris along its base. This acts like sandpaper, grinding mountains down and carving valleys into wide U-shapes. Glaciers can polish rock surfaces, leave long scratches called striations, and deposit piles of sediment known as moraines. Many landscapes you see today were shaped by ice that vanished long ago. Some lakes exist because glaciers carved deep basins and later melted, filling them with water.
Some fertile plains were formed from glacial deposits ground into fine soil. Even coastlines were altered when massive ice sheets locked up ocean water, lowering sea levels and exposing land bridges. Ice also affects Earth in another way. When huge ice sheets grow, their weight presses down on the crust. The land can sink under the pressure. When the ice melts, the land slowly rises again, a process called isostatic rebound. In some places, the ground is still lifting today, thousands of years after the last major ice age ended. So ice is both memory and motion. It stores the past and reshapes the present. And as we continue, we will leave the frozen archives behind and drift into another quiet force of change, the slow chemistry of rock weathering, where even mountains dissolve grain by grain into the sea.
Even the strongest mountains are not permanent. No matter how tall they rise, no matter how ancient they seem, they are slowly being broken down, not by sudden explosions, but by quiet chemistry and patient time. This process is called weathering, and it is one of the most gentle yet unstoppable forces on Earth. Weathering begins the moment rock is exposed to air and water. Rain seeps into tiny cracks. Temperature changes cause expansion and contraction. Ice forms inside fractures and widens them, slowly prying the rock apart. Wind carries sand that scratches surfaces over time. These physical forces weaken rock, but chemistry goes even deeper. Water is not just a liquid, it is a chemical tool. When rain falls through the atmosphere, it absorbs carbon dioxide. This creates a weak carbonic acid, gentle but persistent. When this slightly acidic water touches certain rocks, it reacts with minerals, slowly dissolving them. Limestone, for example, is especially vulnerable. Over long periods, water can dissolve entire caves and carve underground rivers. This is how many of Earth's cave systems form. They are not created by earthquakes or volcanic eruptions, but by slow dripping water working silently for thousands of years. Stalactites and stalagmites grow in darkness, building mineral shapes drop by drop, each one a tiny record of the water's journey. Weathering also connects deeply to Earth's climate. When rocks break down, they can remove carbon dioxide from the atmosphere. Certain minerals react with carbon dioxide and lock it away in new compounds that eventually wash into the ocean. Over millions of years, this acts as a natural thermostat. If carbon dioxide rises, temperatures warm, rainfall increases, and weathering speeds up. That weathering then pulls more carbon dioxide out of the air, cooling the planet again. It is a slow balancing system, not perfect, but powerful across deep time. The products of weathering do not stay in place. Rivers carry them away. Grains of sand, dissolved minerals, and tiny particles of clay travel downstream toward the sea. Over time, these sediments build deltas, floodplains, and new coastlines. Some settle into quiet basins, forming layers that harden into sedimentary rock. Each layer is like a page, capturing the environment of its time. Sometimes these layers preserve fossils. A leaf, a shell, or a footprint can be buried quickly and sealed away, surviving as stone evidence of life that once moved through an ancient world. Fossils are not only bones, they are impressions, traces, and chemical signatures, all locked into sediment like whispers from vanished ecosystems. Sedimentary layers can also record disasters. A sudden flood may leave a thick band of sand. A volcanic eruption may drop ash into the mud. A meteor impact may scatter unusual minerals. Over time, these layers become stacked histories, and the deeper you go, the farther back you travel. Eventually, those sediments may be buried deeply enough to transform. Pressure and heat can change rock into metamorphic forms, compressing minerals into new patterns. If the rock sinks even deeper, it may melt and become magma again, returning to the cycle of volcanic creation. So Earth is never finished. Mountains rise, then dissolve. Rivers carry the remains. Oceans bury the fragments. Heat reshapes them, and the planet begins again. And next, we will follow those sediments into the deep sea, where Earth hides some of its most mysterious and silent landscapes beneath the waves. Far below the ocean's surface, beyond the reach of sunlight, the seafloor spreads out like another world. It is not flat and peaceful the way many people imagine. It is rugged, scarred, and full of dramatic features shaped by tectonic motion and slow sedimentation. Some parts of the seafloor are covered in thick blankets of mud, built grain by grain over millions of years. Other regions are cracked open by volcanic ridges where new crust forms. And in certain places, the ocean floor drops suddenly into deep trenches, narrow valleys so steep and dark that they feel like wounds in the planet's surface. These trenches exist where one tectonic plate bends downward and slides beneath another. The descending plate sinks into the mantle in a slow process of recycling. Above it, the surface plate can be squeezed, fractured, and lifted, creating chains of earthquakes and volcanoes. The deepest trenches are deeper than most mountains are tall. In the Mariana Trench, for example, the seafloor plunges so far down that if Mount Everest were placed inside, its peak would still be underwater. At those depths, pressure becomes crushing. Every inch downward adds more force until the water above presses with a weight that would destroy most objects instantly. And yet, life exists even there. Deep-sea organisms survive by adapting to darkness, cold, and extreme pressure. Some feed on particles that drift down like snow from the surface. Others rely on chemical energy from vents and seeps. In these places, Earth feels alien, as if the planet has hidden an entire ecosystem where almost no one can see. The deep ocean is also a graveyard of history. Sediments settle onto the seafloor constantly, preserving shells, microfossils, and chemical signals of past climates. In certain areas, layers of sediment build so slowly that a single centimeter can represent centuries. These layers can reveal ancient ocean temperatures, shifts in sea level, and changes in Earth's atmosphere. The seafloor also contains strange formations made from minerals that grow incredibly slowly. Manganese nodules, for example, are rounded lumps that form as dissolved metals precipitate around a small core, sometimes a fragment of bone or a grain of sand. They can take millions of years to grow to the size of a potato. It is a reminder that deep time is always at work, even in silence. The ocean floor hides scars from impacts as well. On land, impact craters can be eroded or covered by forests. In the ocean, craters can be buried under thick sediments, becoming nearly invisible. Scientists sometimes detect them only through gravity measurements or seismic imaging. Earth's surface is constantly rewriting itself, and the ocean is one of its most effective editors. Sometimes, underwater landslides occur, sending massive volumes of sediment sliding down continental slopes. These landslides can trigger tsunamis even without an earthquake. The deep sea may look calm from above, but it is capable of sudden movement. And beneath all of this, the seafloor is slowly spreading, pushing continents apart, while trenches swallow old crust in return. Earth's surface is a loop, endlessly creating and consuming itself. Next, we will drift back toward the continents and explore one of the most delicate balances on the planet: the way soil forms, the way nutrients move, and how landscapes quietly become places where life can grow.
When you walk across the land, it is easy to forget that soil is not simply dirt. Soil is one of the most complex and precious materials on Earth. It is a living mixture of minerals, water, air, and organic matter. And it forms so slowly that a single inch can take hundreds or even thousands of years to develop. Soil begins as rock. Wind, rain, freezing temperatures, and chemical reactions slowly break stone into smaller particles. Over time, these particles mix with decaying leaves, dead roots, and microorganisms. Bacteria and fungi help transform organic material into nutrients. Worms and insects churn the ground, opening pathways for air and water. The result is a thin, fragile layer where plants can grow and ecosystems can take root. In many ways, soil is the skin of the continents. And like skin, it can be damaged. Erosion can remove soil faster than it forms. Heavy rainfall can wash it away. Strong winds can lift it into the atmosphere. Rivers can carry it downstream. When vegetation is removed, the ground loses its protection and the land becomes vulnerable. Over long periods, this can change entire landscapes, turning fertile regions into dry, fragile terrain. Yet erosion is not always destructive. It is also creative. The sediment carried by rivers is what builds deltas. It is what forms floodplains. It is what creates rich farmland in many parts of the world. When a river floods, it spreads fine, nutrient-rich particles across the land. This is why ancient civilizations often formed along rivers. The river did not only provide water, it provided fresh soil. Earth moves nutrients in cycles. Minerals weather out of rocks, travel through soil, feed plants, and return to the ground when organisms die. Some nutrients wash into the ocean, where they feed plankton and marine life. Some become buried in sediments and locked away for ages. Over time, tectonic uplift can raise those sediments back into mountains, exposing them again to weathering and restarting the cycle. Even desert dust plays a role. Fine particles lifted from dry regions can travel thousands of miles, delivering iron and phosphorus to distant forests and oceans. What seems like an empty desert can quietly feed ecosystems far away. The planet is constantly sharing its materials, redistributing minerals across the surface like a slow global exchange. Soil also preserves memory. Buried layers can reveal past climates. A thick, dark soil horizon may suggest a time when grasslands dominated. A layer rich in charcoal may hint at ancient wildfires. Volcanic ash deposits can become part of the soil, adding minerals that make the land unusually fertile. This is why regions near volcanoes, despite the danger, can support productive agriculture. In some places, soil holds the fingerprints of ancient ice ages. Glaciers ground rock into fine powder and left behind thick deposits. When the ice melted, it created plains of fertile sediment. These glacial soils helped shape where forests grew, where rivers flowed, and where people eventually settled. Soil may seem ordinary, but it is one of Earth's quiet miracles. It connects rock to life, geology to ecosystems, and deep time to the food we eat today.
And as we continue, we will move into another hidden archive of Earth science, the world of fossils, where stone preserves the outlines of vanished creatures, and the planet's history of life is written in silent layers. Fossils are Earth's quiet storytellers. They are not just bones trapped in stone. They are traces of life preserved by chance, sealed away in sediment and carried forward through time. A fossil is a message from a world that no longer exists, a small piece of ancient life that survived long enough to reach the present. Most living things never become fossils. When an animal dies, its body is usually broken down by scavengers, bacteria, and weather. But sometimes the conditions are just right. The organism is buried quickly, protected from oxygen, and covered by sediment before it can fully decay. Over time, layers of mud, sand, or ash harden into rock, and the remains inside begin to change. Minerals seep in through tiny spaces, slowly replacing organic material. Bone becomes stone, shell becomes rock. Even wood can become petrified, its structure preserved in mineral form. Fossils can also be more subtle. A footprint in soft mud can harden and remain. A trail left by a crawling creature can become a preserved trackway. A leaf pressed into wet sediment can leave a detailed imprint, showing veins and edges with astonishing clarity. These are called trace fossils, and they often reveal behavior, not just anatomy. They show where an animal walked, how it moved, and sometimes even how it hunted. Fossils remind us that Earth has been filled with strange and changing life for hundreds of millions of years. Long before humans existed, forests of giant ferns covered the land. In warm, shallow seas, trilobites crawled across the ocean floor. Dinosaurs ruled for an age that lasted far longer than human civilization has existed. Even the animals alive today are only the latest chapter in a much larger story. The layers of rock that hold fossils are like a timeline. The deeper you go, the older the layers become. By studying fossils in different layers, scientists can see patterns of evolution and extinction. They can observe when certain species appeared, when they vanished, and how life responded to changes in climate and geography. Mass extinctions stand out sharply in the fossil record. These are moments when a large portion of life disappeared in a relatively short time. The most famous extinction ended the age of dinosaurs, likely triggered by an asteroid impact. But other mass extinctions occurred as well, caused by volcanic eruptions, shifting oceans, changing oxygen levels, and rapid climate changes. Earth has experienced repeated resets, and life has repeatedly rebuilt itself afterward. Fossils also reveal the movement of continents. Similar fossils have been found on continents now separated by oceans. This helped scientists realize that the continents were once connected. The same ancient plants and animals once lived in regions that are now thousands of miles apart. Fossils became evidence that the world itself had shifted. Some fossils even preserve the chemistry of ancient environments. Tiny marine shells contain oxygen isotope ratios that reveal the temperature of the ocean when the organism lived. This allows scientists to reconstruct ancient climates, showing when the planet was warmer or colder than today. Fossils are not just objects, they are memories. They are proof that Earth is not a stable stage. It is a changing world where landscapes shift, climates swing, and life adapts or disappears. And next, we will explore another force that shapes life and land alike, the movement of groundwater, the hidden rivers beneath the surface that quietly carve, dissolve, and reshape the world from below.
Beneath the surface of Earth, below soil and stone, there is another world moving in silence. It is not made of rivers you can see, but of water traveling slowly through cracks, pores, and hidden channels.
This is groundwater, and it shapes the planet in ways most people never notice. When rain falls, not all of it becomes runoff. Some water flows into streams and rivers, but a large portion sinks into the ground. It seeps downward through soil, passing between grains of sand, through tiny fractures in rock, and into deeper layers where it can be stored for years, centuries, or even longer. These underground water holding layers are called aquifers. Aquifers can be vast, stretching beneath entire regions. Some hold fresh water that feeds wells and springs. Others contain ancient water trapped long ago, sometimes during ice ages when climates were very different. In some deserts, groundwater being pumped today may have fallen as rain tens of thousands of years ago, preserved underground like a hidden relic of a wetter world. Groundwater moves slowly. Unlike a river, it does not rush. It creeps through the earth at a pace that can be measured in feet per day, or sometimes only inches. But over long periods, that slow movement becomes powerful. Groundwater dissolves rock. As water travels, it picks up carbon dioxide from soil and becomes slightly acidic. That weak acidity allows it to break down minerals. In limestone regions, groundwater can carve caves, tunnels, and underground chambers. It dissolves rock grain by grain, drop by drop, widening cracks until entire cave systems form. Inside caves, water continues its slow artistry. When mineral-rich water drips from the ceiling, it leaves behind tiny deposits of calcite. Over centuries, these deposits grow into stalactites hanging downward. On the floor, stalagmites rise upward as drops fall and evaporate. Each one grows so slowly that a human lifetime may not notice the change, but the cave itself is always evolving. Sometimes groundwater creates sudden, dramatic events. If a cave roof collapses, the land above can fall into the empty space, forming a sinkhole. Sinkholes can appear without warning, swallowing roads, trees, and buildings. They are reminders that the ground beneath us is not always solid. It can be hollow, fragile, and quietly changing. Groundwater also connects to rivers. Many streams are fed by springs where groundwater reaches the surface. Even during dry seasons, when rain is scarce, groundwater can keep rivers flowing. It acts as a hidden reservoir that releases water slowly over time. In this way, groundwater is part of the planet's water balance, linking rainfall to long-term stability. Some groundwater is heated by Earth's internal energy. When water travels deep enough, it can warm and rise back up as hot springs. In volcanic regions, it can become extremely hot, producing geysers that erupt in bursts of steam and boiling water. These features are powered by the same heat that drives volcanoes, but expressed through water instead of lava. Groundwater can also carry minerals. It can deposit gold, quartz, and other valuable materials in veins as it cools and reacts with rock. Entire ore deposits can form through slow underground circulation. So, beneath every landscape, water is moving, dissolving, storing, and reshaping. And as we continue, we will move from hidden water to something equally invisible but deeply influential: the way Earth's rotation and gravity shape oceans, winds, and even the rhythm of life itself. Earth does not only change through rock and water. It is also shaped by invisible forces that act quietly every second. Gravity pulls, rotation spins, and together they create patterns that control oceans, winds, and even the rhythm of day and night. Gravity is the force that holds everything together. It keeps oceans pressed against the planet, keeps the atmosphere from drifting into space, and gives weight to every mountain and stone. But gravity is not perfectly equal everywhere. Earth is not a perfect sphere. It bulges slightly at the equator because of rotation, and different regions contain different densities of rock beneath the surface. Because of this, gravity varies slightly from place to place. Scientists can measure these tiny differences using satellites, creating maps that reveal hidden structures underground. A mountain range may have deep roots. A buried crater may create a subtle gravitational dip. Even the movement of magma can change gravity in a detectable way. In this sense, gravity becomes a tool for reading Earth's hidden interior. Rotation shapes the planet as well. Because Earth spins, moving air and water are deflected. This effect is called the Coriolis effect. In the northern hemisphere, moving objects tend to curve to the right. In the southern hemisphere, they curve to the left. This is why hurricanes spin in opposite directions depending on which hemisphere they form in. The Coriolis effect helps organize global wind patterns, creating trade winds near the equator and westerlies farther north and south. It also influences ocean currents, guiding water into large rotating systems called gyres. These gyres move heat across the planet, helping balance climate. Even the oceans respond to Earth's rotation in subtle ways. Tides are one of the most familiar expressions of gravity. The moon's gravitational pull raises bulges in Earth's oceans. As Earth rotates, coastlines pass through these bulges, creating the rise and fall of sea level. The sun also contributes to tides, though the moon has a stronger effect because it is much closer. When the sun, moon, and Earth line up, tides become stronger. These are called spring tides. When the moon is at a right angle to the sun, tides become weaker, known as neap tides. This rhythm has repeated for billions of years, shaping shorelines, moving sediments, and influencing coastal ecosystems. Tides are not only about water height, they create currents. As water flows in and out of bays and channels, it can carve coastlines and mix nutrients into marine environments. In some places, tides are strong enough to generate power. In others, they create tidal bores, walls of water that travel upstream like moving waves. The moon's influence goes even deeper. Many scientists believe the moon also stabilizes Earth's axial tilt. Without the moon, Earth's tilt might wobble far more dramatically over time, leading to extreme climate swings. With the moon acting as a gravitational anchor, Earth's seasons remain relatively stable, creating a predictable rhythm that life has adapted to. It is remarkable to think that the moon may exist because of a violent beginning. One leading theory suggests that a Mars-sized object collided with early Earth, blasting material into orbit. That debris eventually formed the moon. If this is true, then Earth and Moon share a connected origin, like two parts of the same ancient event. Gravity and rotation, tides and time all work together quietly. And next, we will explore another kind of motion, not the movement of water or air, but the movement of heat itself, rising through the mantle and shaping continents from below.
Heat is one of Earth's most constant forces. It rises from the planet's interior like a slow, invisible breath, shaping continents, fueling volcanoes, and driving the movement of tectonic plates. Even though the surface feels cool and stable, Earth still carries ancient warmth from its formation, along with heat produced by radioactive decay deep inside. This heat does not stay trapped.
It moves upward through the mantle in a process called convection. Hot material becomes lighter and rises. Cooler material becomes denser and sinks. Over long periods, this creates slow circulating currents in the mantle, like thick syrup moving inside the planet. These currents are one of the reasons Earth's crust is constantly shifting. In some places, rising heat forms mantle plumes. A mantle plume is a column of unusually hot rock rising from deep within the mantle. When it reaches the surface, it can create volcanic hotspots. Unlike volcanoes along plate boundaries, hotspots can form in the middle of a tectonic plate. The plate moves over the plume, and as it does, a chain of volcanoes forms behind it. Hawaii is a famous example. The Hawaiian Islands were built as the Pacific Plate slowly drifted over a hotspot. The youngest and most active volcanoes are at one end of the chain, while older islands, worn down by erosion, stretch away in a line. The islands are like stepping stones marking the direction of plate motion, each one a reminder that the crust is never fixed. Heat also reshapes continents through uplift. When hot mantle material rises beneath a region, it can push the crust upward, creating high plateaus or domed landscapes. This uplift can change the flow of rivers, alter rainfall patterns, and create new environments. Sometimes it can even lead to rifting, where the crust begins to pull apart. Rifting is how oceans are born. When a continent stretches and fractures, magma can rise into the cracks, forming volcanic valleys. Over time, the rift can widen until seawater floods in, creating a new ocean basin. The Red Sea is an example of an ocean in the early stages of formation, where Africa and Arabia are slowly separating. Earth's surface is always in transition. Oceans open and close, continents merge and split. The planet rearranges itself over hundreds of millions of years in a slow cycle called the supercontinent cycle. At times in the past, most of Earth's land was joined into a single supercontinent. One of the most famous was Pangaea. When Pangaea existed, the world looked completely different. Coastlines were unfamiliar, ocean currents moved in different patterns, climate zones shifted. Eventually, tectonic forces pulled Pangaea apart, creating the continents we recognize today. This slow reshaping influences life. When continents collide, mountains rise and climates change. When continents separate, new coastlines appear and ocean circulation shifts. Species become isolated and evolve along different paths. Earth's geology and biology are connected, each influencing the other over deep time. Even the seafloor tells this story. As new crust forms at ridges, it spreads outward. The rock carries magnetic minerals that align with Earth's magnetic field. Because the magnetic field reverses over time, the seafloor preserves stripes of alternating magnetic orientation. These stripes are like barcodes, proving that the ocean floor is spreading and recording the history of Earth's magnetic changes. Heat drives this entire system, quietly shaping the world. And next, we will explore the hidden chemistry of Earth's oceans and rocks, where minerals dissolve, reappear, and create cycles that help regulate the planet's atmosphere and long-term stability.
Earth is not only shaped by motion and heat, it is also shaped by chemistry, a slow, invisible exchange between rock, water, air, and life. These chemical cycles are not dramatic like earthquakes or eruptions, but they quietly control the planet's long-term balance. One of the most important of these cycles is the carbon cycle. Carbon moves through Earth in many forms. It exists in the air as carbon dioxide. It exists in oceans as dissolved carbonate. It exists in rocks as limestone. It exists in living things as the building block of cells. And over time, it moves between these places, guided by weathering, biology, and geology. When rain falls, It absorbs carbon dioxide from the atmosphere and becomes slightly acidic. This weak acid reacts with rocks, especially silicate minerals, breaking them down. During this process, carbon dioxide is effectively removed from the air and carried away in dissolved form. Rivers transport these dissolved materials into the ocean, where they can eventually become part of shells and skeletons made by marine organisms. When these organisms die, their shells settle to the sea floor and form thick carbonate sediments. Over millions of years, these sediments harden into limestone. In this way, carbon becomes locked into rock, stored away for ages. But carbon does not stay buried forever. When tectonic plates carry limestone downward into subduction zones, heat and pressure break the rock apart. Carbon dioxide is released again and carried upward through magma. Volcanoes then release it back into the atmosphere. This creates a long geological loop, pulling carbon out of the air through weathering and returning it through volcanism. This slow cycle acts like a thermostat. If carbon dioxide levels rise, Earth warms. Warmer temperatures often increase rainfall, which increases weathering, which removes more carbon dioxide. Over very long timescales, this helps stabilize climate. It is not a perfect system, but it has helped Earth avoid extremes for much of its history. The oceans play a major role in this balance. They absorb large amounts of carbon dioxide, storing it in dissolved form. Some of it becomes part of marine life. Some of it sinks into deeper water. Ocean circulation helps distribute carbon across the planet. The ocean is not only a reservoir of water, it is a reservoir of chemistry. The ocean also holds another powerful chemical system: oxygen. Oxygen did not always fill Earth's atmosphere. Early Earth had very little free oxygen. Much of the planet's early life was anaerobic, living without oxygen. Then, long ago, photosynthetic microbes began producing oxygen as a waste product. Over time, oxygen slowly accumulated, transforming the atmosphere and making complex life possible. This event is known as the Great Oxidation Event. It changed Earth completely. It altered minerals, changed ocean chemistry, and forced life to adapt or vanish. Many organisms could not survive the new oxygen-rich environment. Others evolved to use oxygen for energy, opening the door to larger and more complex forms of life. Even today, oxygen continues to cycle. Plants and algae produce it. Animals consume it. Organic matter buried in sediments can store carbon, indirectly allowing oxygen to remain in the atmosphere. The balance between these processes shapes the air we breathe. Earth's chemistry is not separate from geology, it is part of the same system. Rocks influence oceans, oceans influence air, air influences life, life influences rocks. The planet is a network of cycles, each one quietly connected to another. And next, we will move toward one of the most dramatic results of Earth's chemistry and climate, the formation of deserts, storms, and the shifting patterns of dryness and rainfall that shape entire continents.
Across Earth's surface, dryness and moisture are not evenly shared. Some regions receive endless rainfall, covered in thick forests and rivers. Others remain dry for years, shaped by wind and sun into deserts that seem almost timeless. But deserts are not empty wastelands. They are living landscapes formed by climate patterns, ocean currents, and the slow movement of air. A desert is not defined only by heat. It is defined by lack of precipitation. Some deserts are hot, like the Sahara. Others are cold, like parts of Antarctica. In both cases, the key is that very little water falls from the sky. The atmosphere above these regions tends to suppress cloud formation, keeping moisture locked away elsewhere. One reason deserts form is global circulation. Near the equator, sunlight is strong. Warm air rises, carrying moisture upward. As it rises, it cools, and water vapor condenses into heavy rainfall. This creates tropical rain belts. But the air that rises near the equator must eventually sink somewhere else. As it moves toward higher latitudes, it cools and dries. When it sinks around 30 degrees north and south, it compresses and warms, making clouds less likely to form. These sinking zones create many of the world's major deserts. Ocean currents also shape dryness. Cold ocean currents cool the air above them. Cooler air holds less moisture, and it often creates stable conditions that prevent rain. This is why deserts like the Atacama in South America exist near the coast, even though they are close to the ocean. The sea is there, but the air above it does not easily rise to form clouds. Mountains create deserts too. When moist air is forced upward over a mountain range, it cools and releases its water as rain or snow. By the time the air descends on the other side, it is much drier. This creates a rain shadow desert. The Great Basin in the United States is partly shaped by this effect, as mountains block moisture from reaching inland regions. Deserts are shaped strongly by wind. Without thick vegetation, the surface is exposed. Winds can lift fine dust and sand, carrying it across continents. Over time, wind sculpts dunes into shifting waves. It polishes rocks into smooth forms. It can even carve stone into sharp ridges. These wind-shaped landscapes are slow-moving, but they never stop changing. Desert dust is not useless. It can travel across oceans, fertilizing distant ecosystems. Dust from Africa, for example, can drift over the Atlantic and deliver nutrients to the Amazon rainforest. Tiny mineral particles carry phosphorus and iron, feeding soils that would otherwise be depleted. In this way, deserts become part of Earth's nutrient network, quietly supporting life far away. Deserts also preserve history. Because there is less water to erase features, ancient riverbeds and fossil landscapes can remain visible for long periods. Some deserts contain dried lake basins that prove they were once wetter. Others contain salt flats that mark vanished seas. Dryness and moisture shift over time. A region that is desert today may have been grassland in the past. Climate cycles, changing ocean currents, and tectonic uplift can all alter rainfall patterns. Earth is never locked into one climate state. And next, we will drift into storms, hurricanes, and the restless atmosphere, exploring how heat and water can combine into some of the most powerful forces on the planet.
Storms are Earth's way of moving energy. They form when heat and moisture build up in the atmosphere, creating imbalance. The planet does not like imbalance. It responds by shifting air, lifting water vapor, and releasing stored energy through wind, rain, and thunder. A storm begins with warm air. Warm air is lighter than cold air, so it rises. As it rises, it expands and cools. Cooler air cannot hold as much water vapor, so the vapor condenses into droplets, forming clouds. That condensation releases latent heat, a hidden form of energy stored inside water vapor. When released, it warms the rising air even more, allowing it to rise higher, creating stronger upward motion. This is why thunderstorms can grow so tall. Some storm clouds reach the upper atmosphere, towering like mountains made of vapor. Inside them, droplets collide, freeze, melt, and freeze again. This creates hail. It also creates charge separation, building electrical tension until lightning flashes, releasing energy in an instant. Lightning is not just a bright bolt. It is a channel of plasma hotter than the surface of the sun, formed in a fraction of a second. Thunder is the sound of air expanding violently after being superheated. What seems like a peaceful rain cloud from a distance can be a powerful machine of physics inside. On a larger scale, storms can organize into hurricanes. Hurricanes form over warm ocean water. The sea surface must be warm enough to supply large amounts of evaporation. Moist air rises, condenses, and releases heat, fueling the system. As air rushes inward to replace the rising air, Earth's rotation deflects the flow, causing the storm to spin. A hurricane is a heat engine. At its center is the eye, a calm region of sinking air. Surrounding the eye is the eye wall, where the strongest winds and heaviest rain occur. From above, hurricanes look almost beautiful, spiraling patterns of cloud bands stretching across the ocean. But beneath that beauty is immense destructive power. Hurricanes can move huge amounts of water. Storm surges push seawater onto land, flooding coastlines. Heavy rainfall can overwhelm rivers and cities. Wind can strip roofs and snap trees. Yet, hurricanes are also part of Earth's balance. They transfer heat from tropical oceans toward higher latitudes. They mix ocean waters, stirring nutrients from deeper layers. They are destructive, but they are also part of the planet's energy circulation. Tornadoes are another form of storm intensity. They form when strong wind shear creates rotating columns of air inside thunderstorms. When that rotation tightens and touches the ground, a tornado is born. Tornadoes are smaller than hurricanes, but can be even more violent, with winds capable of lifting cars and tearing buildings apart. Storms also shape geology. Rainfall triggers landslides. Floods carry sediment and carve channels. Lightning can fuse sand into glassy tubes called fulgurites. Even windstorms can transport dust that becomes part of soil elsewhere. The atmosphere is not separate from the land. It constantly reshapes it. And as we continue, we will move into a quieter side of Earth science again, drifting toward the slow, deep processes that create earthquakes, faults, and the trembling boundaries where continents meet and the planet releases its stored tension.
Earthquakes are one of the clearest reminders that Earth is alive beneath the surface. They do not happen because the planet is breaking apart. They happen because the planet is constantly moving, and sometimes that motion becomes stuck. Tectonic plates drift slowly across the mantle, but their edges do not glide smoothly. Along plate boundaries, rocks press together with enormous force. Friction locks them in place. Stress builds quietly, year after year, sometimes for centuries. The ground above may seem stable, but deep below, the crust is storing tension like a bent spring. Then, suddenly, the rock slips. That release sends vibrations through the earth in all directions. These vibrations are seismic waves, and they travel through rock the way sound travels through air, except far faster and with far more power. There are different types of seismic waves. Some move through the interior of Earth, compressing and stretching rock. Others travel along the surface, rolling the ground in waves. Surface waves often cause the most damage because they shake buildings and landscapes more strongly. Earthquakes can happen in different tectonic settings. At subduction zones, where one plate dives beneath another, earthquakes can be massive. These are the boundaries that produce some of the strongest quakes ever recorded. When the seafloor suddenly lifts or drops during such a quake, it can push the ocean above it, creating a tsunami that travels across entire oceans. At transform boundaries, plates slide past each other sideways. The San Andreas Fault in California is one of the most famous examples. Here, stress builds until the fault suddenly shifts, producing sharp ground motion. At divergent boundaries, plates pull apart. Earthquakes occur there too, though they are often smaller. These quakes can accompany volcanic activity as magma rises through widening cracks. Faults are not always visible. Some faults are hidden beneath soil, forests, or ocean water. Others cut clearly across the land, forming scarps where the ground has shifted. Over long periods, repeated earthquakes can shape landscapes. Valleys can form along fault lines. Rivers can be offset. Hills can rise where crust is compressed. Earthquakes also reveal the interior of Earth. Because seismic waves travel differently through solid and liquid materials, scientists can use them to map layers inside the planet. This is how we know Earth has a solid inner core and a liquid outer core. Seismic waves act like a natural ultrasound, allowing us to study a world we cannot directly reach. Sometimes earthquakes occur far from plate boundaries. These are called intraplate earthquakes. They can happen when ancient faults deep inside a plate reactivate under stress. They are less common, but they remind us that Earth's crust carries old scars that can awaken again. After a major earthquake, the ground often continues to shift. Aftershocks ripple through the region as the crust adjusts. In some cases, land can rise or sink permanently. Coastlines may change shape. Rivers may alter their course. The landscape remembers the quake. Earthquakes can feel sudden and violent, but they are part of a slow process. They are the release of motion that has been building invisibly for a long time. And next, we will drift into the deep ocean again, exploring how earthquakes and tectonic movement create volcanic island chains, hidden arcs, and some of the most dramatic geology on the planet.
When tectonic plates collide in the ocean, they create some of the most dramatic structures on Earth. Yet most of them remain hidden beneath miles of water. These regions are not only zones of earthquakes, they are also zones of volcanoes, where Earth's crust melts and rises again, building new land from the deep. At subduction zones, an oceanic plate bends downward and sinks beneath another plate. As it descends, it carries water trapped inside its minerals and sediments. Deep in the mantle, heat and pressure force that water out. The released water lowers the melting point of surrounding rock, allowing magma to form. That magma is lighter than solid rock, so it rises. As it rises through the crust, it can collect in chambers, building pressure. Eventually, it erupts.
This is how volcanic arcs form, long chains of volcanoes that curve along subduction boundaries. Some volcanic arcs rise above sea level and form island chains. Japan is part of a volcanic arc. So is Indonesia. The Aleutian Islands stretch like stepping stones across the North Pacific, shaped by subduction and eruption over millions of years. These islands exist because one plate is being swallowed beneath another, creating a line of fire along the ocean's edge. Many volcanic arcs remain underwater. Submarine volcanoes can erupt without anyone seeing them, building cones and ridges in darkness. Over time, repeated eruptions can raise the seafloor higher until an island finally breaks the surface. A new island may appear suddenly, steaming and raw, surrounded by ash and floating pumice. Pumice is volcanic rock filled with bubbles. It forms when gas-rich magma erupts and cools quickly, trapping air pockets inside. Because of these bubbles, pumice can float. After certain eruptions, huge rafts of pumice drift across the ocean, carrying tiny organisms and seeds. These rafts can travel for months, sometimes reaching distant shores, acting like floating islands of stone. Volcanic arcs also influence the ocean itself. Ash falls into the water, adding minerals. Hydrothermal vents form near underwater volcanoes, releasing heated fluids rich in chemicals. These vents can support life without sunlight, creating ecosystems based on chemosynthesis. In these dark regions, microbes use chemical energy instead of light, forming the foundation for strange communities of worms, crabs, and other organisms. Subduction zones create deep trenches, but they also create mountain ranges. When oceanic crust dives downward, it can scrape sediments off the seafloor. These sediments pile up and compress into ridges called accretionary prisms. Over time, these ridges can become uplifted land. This is one way coastlines grow outward, built from sediments that were once ocean floor. Volcanic arcs can also affect climate. Large eruptions can inject sulfur gases into the stratosphere, creating aerosols that reflect sunlight and cool the planet temporarily. Some eruptions have altered global weather patterns for years, leaving evidence in tree rings and ice cores. So, the ocean's volcanic boundaries are not isolated. They connect deep Earth to the atmosphere, geology to biology, and seafloor motion to the surface world. And as we continue, we will move from volcanic islands to another quiet mystery, the way Earth's surface can preserve ancient shorelines, showing where oceans once stood and how sea level has risen and fallen across deep time.
The shoreline you know today is only a temporary outline. Coastlines feel permanent because they are familiar, but Earth's oceans have risen and fallen many times. Sea level is not fixed. It changes with climate, ice, tectonic uplift, and even the slow shifting of the seafloor itself. During ice ages, enormous volumes of water become locked into glaciers and ice sheets. When that happens, sea level drops. Vast areas of continental shelf that are underwater today become exposed land. Ancient coastlines move outward. Islands connect to continents. Land bridges appear, allowing animals and humans to migrate across regions that would later vanish beneath the sea. When the climate warms and ice melts, the opposite happens. Sea level rises, water floods lowlands, coastlines retreat inward, entire landscapes disappear beneath waves. The last major ice age ended around 12,000 years ago. When glaciers melted, sea level rose dramatically, reshaping coastlines across the world. Many ancient human settlements that once stood near the shore are now underwater, buried beneath sediment. Earth has clues that reveal these past sea levels. Raised beaches, for example, are shorelines that now sit far above the ocean. They can form when land is uplifted by tectonic forces, or when ice sheets melt and the crust rebounds upward. In some regions, the ground is still rising today after being freed from the weight of ancient glaciers. There are also marine terraces. These are flat, step-like surfaces along coastlines, created when waves cut into rock at a certain sea level. If the land later rises, that old wave-cut platform is lifted above the water, preserved like a fossil shoreline. A coastline can hold multiple terraces, stacked like stairs, each one marking a different period when sea level remained stable long enough to carve the land. Sea level is influenced not only by ice, but by the shape of the ocean basins. Tectonic activity can change how much space the oceans have. When mid-ocean ridges are more active and swollen with hot young crust, they take up more volume, pushing seawater onto continents and raising sea level. When ridges cool and sink, ocean basins deepen and sea level can drop. Even the distribution of water is affected by gravity. Ice sheets pull water toward them slightly because of their mass. When an ice sheet melts, the gravitational pull weakens and water redistributes across the planet. This means sea level rise is not the same everywhere. Some coastlines experience greater change than others. Sea level shifts also influence ecosystems. When oceans rise, salt water can move into freshwater wetlands. Coastal forests may drown. Coral reefs may struggle or adapt, depending on how fast the water changes. When sea level drops, new land emerges, allowing plants and animals to spread outward. These changes can be slow, unfolding over thousands of years, but sometimes they accelerate. Storm surges and tsunamis can temporarily reshape coastlines in hours, moving sand, carving channels, and leaving behind layers that become part of the geological record. Coastlines are places where Earth is always negotiating between land and sea. And next, we will drift into the world of coral reefs, limestone, and the slow building of stone from living creatures, where oceans quietly turn life into rock and preserve it for ages.
In warm, shallow seas, life builds stone. This may sound impossible at first, but it is one of the most remarkable processes on Earth. Coral reefs, shell beds, and limestone cliffs exist because countless small organisms spent their lives turning dissolved minerals into solid structure. The ocean holds calcium and carbonate ions in its water. Many marine creatures use these materials to build shells and skeletons. Corals are among the most famous. A coral reef is not a single organism. It is a massive colony of tiny animals called polyps, each one creating a hard calcium carbonate skeleton beneath itself. Over time, these skeletons stack and expand, forming reefs that can stretch for miles. Corals often live in partnership with microscopic algae that live inside their tissues. These algae provide energy through photosynthesis, which is why most reefs form in clear, shallow water where sunlight can reach. In return, the coral provides shelter and nutrients. This partnership is delicate.
If water temperatures rise too much, corals can become stressed and expel the algae, turning pale in a process known as coral bleaching. A reef is more than a structure. It is a living ecosystem. Reefs support an enormous variety of life. Fish, crustaceans, sea turtles, and countless other organisms depend on them. They act like underwater cities filled with movement and color. But even after a reef dies, it can continue shaping Earth. When reefs are buried under sediment, their calcium carbonate structures can harden into limestone. Over millions of years, limestone deposits can grow thick, forming entire rock layers. Many cliffs and mountain ranges on land were once ancient seafloors built from the remains of marine organisms. The White Cliffs of Dover, for example, are made largely from microscopic shells of plankton that accumulated in the ocean long ago. Each grain of chalk is a fragment of life pressed together into stone. Limestone landscapes have unique features. Because limestone dissolves easily in weak acid, rainwater can carve caves, sinkholes, and underground rivers. Entire regions can become karst landscapes filled with hidden caverns and sudden collapses. In some places, rivers disappear into the ground, traveling through limestone tunnels before emerging again as springs. Limestone also plays a major role in Earth's carbon cycle. When carbon is locked into limestone, it is stored away for long periods. But tectonic forces can bring limestone back into the mantle through subduction. There, heat releases carbon dioxide, which can later escape through volcanic eruptions. In this way, reefs and shells become part of a planet-wide exchange between ocean and atmosphere. The ocean is constantly creating rock through biology. Even small organisms contribute. Foraminifera, tiny single-celled creatures, build shells that settle to the seafloor when they die. Over time, they form thick sediments. Coccolithores, another microscopic group, create tiny plates that become part of chalk deposits. The ocean floor is covered in the remains of invisible builders. This is a quiet kind of geology. No earthquakes are required, no volcanoes erupt. Instead, life slowly deposits layer after layer, turning water into stone. It is strange to think that a mountain can begin as a reef, but Earth is full of transformations like this. What is alive today can become rock tomorrow, and what is rock today may once have been living. And next, we will explore another transformation, the way rivers build deltas and floodplains, shaping coastlines and creating some of the richest ecosystems on the planet.
Rivers are not just streams of water. They are moving sculptors carrying the broken pieces of mountains toward the sea. Every river is part of a larger system, linking rainfall, soil, rock, and ocean into one continuous flow. A river begins high in a landscape, often as melting snow, rain runoff, or springs emerging from underground. At first, it may be small, just a narrow ribbon of water cutting through rock. But as tributaries join, the river grows stronger, collecting water from wider regions. It becomes a living network, branching like veins across the land. As it flows, a river carries sediment. Some of that sediment is fine clay drifting in suspension. Some is sand rolling along the bottom. Some is larger gravel and stones that bounce and scrape the riverbed. This moving sediment acts like a tool. It grinds rock, deepens channels, and shapes valleys. Over time, rivers can carve canyons, cut through mountains and create landscapes that look permanent but are always changing. When a river reaches flatter land, its behavior shifts. The slope becomes gentler and the water slows. With less energy, the river begins to drop its sediment. Sandbars form, curves widen. The river begins to meander, bending back and forth in long loops. Over time, these loops can become extreme, and the river may cut through a narrow neck of land, creating a new, straighter path. The abandoned curve becomes an oxbow lake, a quiet crescent of water left behind as the river moves on. These oxbow lakes are reminders that rivers do not follow fixed routes, they wander. Eventually, a river reaches the sea. Here, its flow slows dramatically. The river can no longer carry as much sediment, so it drops much of its load at the coastline. Over time, this builds a delta, a fan-shaped deposit of sand and mud spreading outward into the ocean. Deltas are some of the most fertile landscapes on Earth. They are rich in nutrients, constantly renewed by fresh sediment. The Nile Delta, the Mississippi Delta, and many others have supported dense ecosystems and human civilizations for thousands of years. Rivers do not only deliver water, they deliver soil. But deltas are also fragile. If a river is dammed or diverted, less sediment reaches the delta. Without new deposits, the land can begin to sink and erode. Waves and storms can cut it away. Rising sea levels can flood low areas. Deltas exist in a balance between deposition and loss, between building and drowning. Floodplains form in a similar way. When rivers overflow their banks, they spread water and fine sediment across nearby land. This sediment is often rich in minerals, creating fertile soils that support forests and agriculture. Floods can be destructive, but they also renew the land, rebuilding the floodplain layer by layer. Rivers also shape coastlines through long-shore drift. When sediment reaches the ocean, waves can move it sideways along the shore, building beaches, sand spits, and barrier islands. These features shift constantly, rearranged by storms and tides. A coastline is not fixed. It is an active boundary where river sediment, ocean waves, and sea level changes compete for control. And next, we will drift toward the quietest rivers of all, the slow currents of ice, exploring how glaciers move, melt, and leave behind landscapes that still carry their fingerprints today. Ice may seem still, but glaciers are always moving. They are slow rivers of frozen water flowing under their own weight across valleys and plains. Their movement is so gradual that you cannot watch it happen, but over years and centuries, glaciers reshape entire continents. A glacier begins when snow accumulates faster than it melts. In cold regions or high mountains, snowfall piles up year after year. The lower layers are compressed by the weight above. Air is squeezed out. Snow turns into dense ice. Over time, the ice becomes thick enough to begin flowing downhill, pulled by gravity. Glacial movement happens in two main ways. The ice can deform internally, with layers slowly sliding past each other. It can also slide along the ground beneath it, especially when meltwater lubricates the base. This movement allows glaciers to travel, even though they appear solid. As glaciers move, they carry rock. They pluck stones from mountainsides and drag them along the ground, grinding the surface like sandpaper. This process carves deep valleys into wide U-shaped valleys, different from the sharp V-shaped valleys created by rivers. Glaciers can also carve bowl-shaped depressions called cirques and leave behind sharp ridges known as aretes, where two glaciers once scraped away opposite sides of a mountain. When glaciers melt, they leave evidence everywhere. They deposit piles of unsorted sediment called till, a mixture of clay, sand, gravel, and boulders. These deposits can form moraines, ridges marking where the glacier once stood. Some moraines stretch for miles, like frozen footprints left behind after the ice retreated. Glaciers also create strange isolated boulders. These are called glacial erratics, rocks carried far from their original location and dropped when the ice melted. A single boulder might sit alone in a field, completely different from the surrounding bedrock, a quiet clue that ice once covered the land. During the last ice age, massive ice sheets covered large portions of North America, Europe, and Asia. Sea levels dropped because so much water was locked into ice. When the climate warmed, the ice sheets melted and sea levels rose again. Coastlines shifted, lakes formed, rivers changed direction, entire ecosystems relocated. Some of the Great Lakes were shaped by glacial activity. Ice carved deep basins, and when it melted, water filled the depressions. Many smaller lakes and wetlands formed the same way, leaving landscapes dotted with water like scattered mirrors. Glaciers also affect Earth's crust. A thick ice sheet is heavy enough to press the land downward. When the ice melts, the land slowly rises back up. This rebound can continue for thousands of years. In some regions, the ground is still lifting today, adjusting long after the ice has gone. Ice also stores climate history. In ice cores, scientists find trapped air bubbles that preserve ancient atmospheres. They find layers of ash from volcanic eruptions. They find dust from deserts, showing wind patterns from long ago. Glacial ice is both a sculptor and an archive. And as we move forward, we will explore another kind of archive hidden in stone itself, the record of ancient magnetic reversals and the way Earth's changing field is written into the crust like a slow-moving code. Earth's magnetic field is invisible, but it leaves fingerprints in stone. Across the seafloor and inside ancient lava flows, there is a quiet record of something remarkable. Over deep time, Earth's magnetic field has flipped. North has become south, south has become north, and this reversal has happened many times. When molten rock cools, it becomes a kind of memory. Lava contains tiny magnetic minerals such as magnetite. While the lava is still hot and liquid, these minerals move freely. But as the rock cools and solidifies, the minerals lock into place. They align with the direction of Earth's magnetic field at that moment. This means that a cooled lava flow can preserve the magnetic orientation of the planet like a frozen compass. On land, lava flows preserve magnetic history in scattered layers, but the most striking record lies beneath the oceans. At mid-ocean ridges, new seafloor is constantly forming. Magma arises, cools, and hardens into basalt. As it cools, its magnetic minerals align with Earth's field. Then the seafloor spreads outward on both sides of the ridge, carrying that magnetic pattern away like a moving conveyor belt. Because Earth's magnetic field reverses over time, the seafloor becomes striped. One band of rock forms during a normal polarity.
Another band forms during reversed polarity. As spreading continues, the ocean floor develops symmetrical magnetic stripes on either side of the ridge, like a barcode stretching across the seafloor. When scientists first discovered these patterns, they were stunned. The stripes were clear evidence that the seafloor was spreading and that new crust was being created continuously. It confirmed plate tectonics in a way that could not be ignored. The ocean floor was not ancient and unchanging. It was young, active, and constantly renewed. Magnetic reversals themselves are still not fully understood. They are linked to the movement of liquid iron in Earth's outer core, where the geodynamo generates the magnetic field. The field is not perfectly stable. It shifts and drifts. Over time, it can weaken and reorganize. Eventually, the poles switch. These reversals do not happen in a single day. They unfold slowly over thousands of years. During a reversal, the magnetic field may become weaker and more complex, with multiple poles appearing temporarily. Then the field strengthens again, but in the opposite direction. A magnetic reversal does not necessarily mean disaster. Life has survived many of them. The atmosphere still provides protection from radiation, and Earth's field does not disappear completely. But a weaker field could allow more solar particles to reach the upper atmosphere, increasing auroras and potentially affecting satellites and power systems, if such an event occurred today. The magnetic record is also used as a geological clock. By matching magnetic patterns in rocks with known reversal timelines, scientists can estimate the age of seafloor and volcanic layers. This helps reconstruct the movement of continents through time. So, beneath the ocean, Earth carries a coded history of its own shifting magnetism, written in stone, hidden in darkness, yet readable to those who know where to look. And next, we will explore the quietest kind of timekeeping on Earth, the way tree rings, coral bands, and sediment layers record the passing of years like natural calendars built into the planet itself.
Not all records of Earth's history are hidden deep underground. Some of the most beautiful timelines grow quietly in the living world. Trees, corals, and sediments all carry patterns that mark the passing of time, like natural calendars created by the planet itself. A tree is more than wood and leaves. It is a memory of seasons. In many climates, trees grow faster in warm, wet months and slower in cold or dry months. This creates growth rings. Each year, a tree forms a new ring with lighter wood from rapid growth and darker wood from slower growth. If you cut through a trunk, the rings appear like circles spreading outward, each one representing a year of the tree's life. By studying these rings, scientists can learn about past environments. A wide ring may indicate a year of good rainfall and healthy growth. A narrow ring may suggest drought or stress. Rings can even show evidence of wildfires, insect outbreaks, or sudden cooling events caused by volcanic eruptions. Some trees live for thousands of years, providing long records of climate patterns. This science is called dendrochronology. In the ocean, corals provide another kind of timeline. Corals grow in layers, adding new material as they build their skeletons. These layers can form visible bands similar to tree rings. By examining coral growth patterns, scientists can estimate age and study changes in water temperature and chemistry. Corals also store oxygen isotope ratios, which can reveal past ocean conditions. In this way, reefs become living archives of climate history. Sediments record time as well. In lakes,
fine particles settle to the bottom year after year. In some places, seasonal changes create clear layers called varves. A lighter layer may form during summer when biological activity is high, and a darker layer may form during winter when the lake is calmer. Each pair of layers can represent a single year, allowing scientists to count time backward, like reading pages of a book. Sediment layers can also preserve sudden events. A major flood may deposit a thick band of sand. A volcanic eruption may leave ash. A landslide may create a chaotic layer of debris. These layers become signatures of moments when the planet changed quickly. Even ice contains yearly patterns. In polar regions, seasonal snowfall creates layers that can be counted. These layers trap dust and air bubbles, allowing scientists to reconstruct atmospheric conditions from long ago. Some ice records stretch back hundreds of thousands of years, showing cycles of warming and cooling. Earth's history is not stored in one place. It is stored everywhere. The planet leaves clues in wood, in stone, in ice, and in coral. Each archive tells a slightly different story, but together they reveal a world that is constantly shifting. These natural records are especially valuable because they help us understand change. They show that climate has always moved through cycles. They show that droughts have come and gone. They show that storms have shifted and temperatures have risen and fallen. And they also show how sudden disruptions, like volcanic eruptions, can ripple through ecosystems. In a quiet way, Earth is always writing its diary, not with words, but with layers. And as we reach the final stretch of this journey, we will turn our attention to one of the most peaceful but powerful forces of all, the slow, deep movement of time itself, and the way Earth's surface is always becoming something new, even as it carries the memory of what came before. When you step outside and look at the world, it may feel complete, as if the planet has always looked this way. But Earth is never finished. It is always becoming. Every mountain, every ocean, every cloud, and every grain of sand is part of a process that continues even while you sleep. Time is Earth's quiet architect. It works through slow motion rather than sudden change. A coastline may shift only a few inches in a year. A mountain may rise only a tiny fraction. A river may carve its valleys so gradually that no human eye could ever watch it happen. But Earth does not measure in days. It measures in millions of years. And in that scale, even the smallest motion becomes unstoppable. The surface of the planet is constantly being recycled. Rocks are broken down by weathering. Sediments are carried by rivers. They settle into oceans and lakes, forming layers that harden into stone. Those layers may later be buried deep enough to transform into metamorphic rock. And if they sink deeper still, they may melt into magma, returning to the surface again through volcanoes. This is the rock cycle, and it has been running for billions of years. It is one of the most comforting ideas in earth science. Nothing is truly lost, it only changes form. A grain of sand on a beach may have once been part of a mountain peak. A cliff may have once been ocean mud. A fossil shell may one day become a part of a mountain range. Earth is a planet of transformation, constantly reshaping itself through pressure, heat, water, and motion. Even the continents are temporary. They drift, collide, and break apart. Oceans open and close. Supercontinents form and dissolve.
The world map you know is only one arrangement among many. If you could travel far enough into the past, you would not recognize the shapes of the continents. If you could travel far enough into the future, the coastlines would be different again. And through all of it, life adapts. Life has survived ice ages, asteroid impacts, volcanic winters, shifting oceans and changing atmospheres. It has evolved in response to every geological change, turning Earth's surface into a living experiment, unfolding through time. Even the air and oceans are part of this transformation. Oceans absorb carbon dioxide, store heat, and circulate nutrients. The atmosphere carries moisture, forms storms, and protects the surface. Ice sheets grow and melt. Forests expand and retreat. Deserts shift. Everything is connected. Earth is not a collection of separate systems. It is one system. The rock beneath your feet influences the rivers that shape the land. The oceans influence the winds that shape the clouds. The sun influences the temperature that controls ice. And deep inside the planet, heat drives tectonic movement that rebuilds the surface again and again. There is something peaceful in realizing how vast this process is. Your life is a small moment in Earth's story, but you are part of it. You breathe air shaped by geology. You drink water cycled through ancient rock. You stand on continents that have traveled across the planet like slow-moving ships. And as we reach the final part, we will bring these ideas together, gently closing this journey through Earth science, leaving you with the quiet feeling of a planet that never stops moving, yet remains beautifully balanced.
As this quiet journey through Earth science comes to an end, let your mind rest on one simple truth. The planet beneath you is not silent. It is not still. It is always working, always shifting, always reshaping itself in ways so slow that they feel like eternity. Earth is a living system of motion. The continents drift like patient travelers across the mantle. Mountains rise where plates collide, then slowly dissolve under wind and rain. Rivers carve valleys, change direction, and carry the remains of old landscapes toward the sea. The ocean floor spreads outward at ridges, while trenches swallow crust back into the deep, recycling Earth's surface again and again. Even the air above you is part of this movement. The atmosphere circulates heat and moisture, creating clouds, storms, and seasons. The oceans store warmth, move currents, and support life from the surface to the deepest trenches. Ice sheets grow and melt, shaping coastlines and leaving behind clues in frozen layers. Soil forms slowly from broken rock, becoming the fragile foundation for forests and grasslands. And deep below it all, Earth's core continues to stir. A hidden ocean of molten iron flows in darkness, generating a magnetic field that wraps around the planet like an invisible shield. That field deflects solar wind, protecting the atmosphere and allowing life to thrive. Sometimes it paints the sky with auroras, reminding us that Earth is connected to space and the sun's restless energy. The planet holds memories everywhere. In fossils sealed inside stone, we see creatures from vanished worlds. In sediment layers, we find the marks of floods, fires, and ancient seas. In ice cores, we find trapped air from climates long gone. In coral bands and tree rings, we find the quiet record of years passing like gentle footsteps through time. And beyond Earth itself, meteorites fall from space,
carrying grains older than the sun. Even the universe leaves traces here, scattered into our soil and oceans like stardust returned home. All of this can feel immense, but it can also feel calming, because Earth's story is not chaotic, it is patterned, it is cyclical. It is a balance of building and breaking, warming and cooling, rising and sinking. The planet changes, but it does so with a rhythm, like slow breathing. When you look at a mountain, you are seeing pressure and time. When you look at a river, you are seeing gravity and erosion. When you hear the ocean, you are hearing tides shaped by the moon. When you feel the wind, you are feeling sunlight distributed across a spinning world. Everything around you is connected. And even though Earth is powerful, it is also delicate. A thin atmosphere protects life. A narrow range of temperatures allows oceans to remain liquid. A magnetic field shields the planet from space. Life itself helps shape the air, the soil, and the chemistry of the oceans. Earth is both strong and fragile at the same time. So tonight, as you rest, remember that you are sleeping on a planet that has traveled through billions of years of transformation, a planet that continues to change beneath the stars, quietly and endlessly. And while Earth keeps moving, you can let yourself become still. Slow your breathing, relax your body, let your thoughts fade like waves on a distant shore, and allow the planet's calm rhythm to carry you into sleep.